Well, let's take a look at our first part of common probability distributions. First thing we want to look at is the difference between a discrete and a continuous distribution. So our official definitions here is that a probability distribution gives the probabilities of all possible outcomes for a random variable. And it's a discrete distribution if there's a finite number of possible outcomes. I think the mathematicians also allow for a countably infinite number, but that's a little beyond what we need here, so you can think of it as just a specified number of possible outcomes. Now, a continuous distribution has an infinite number of possible outcomes. Well, let's take a look at some examples here. If we look at the number of days next week on which it will rain, that's a discrete random variable because the only values it can take on are 0 through 7. All 7 days, no days, 3 days. Now, if we talk about the amount of rain that will fall next week, that's a continuous random variable. And there's an infinite number of possible outcomes. And that's saying, if we could measure it as precisely as we like, then we can always find a value between two other values. So that's a continuous random variable. When we talk about a probability function, small p of x, gives the probability that a discrete random variable will equal x. So as an example of that, we're given a probability function p of x equals x over 10. And this is for a discrete distribution with 4 possible outcomes, 1, 2, 3, and 4. So the probability of 3 is simply 3 over 10, 30%. And all those add up to 100%. And we know that because 1 plus 2 plus 3 plus 4 equals 10. So when we take the sum of each of those divided by 10, we end up with 100% of the possible outcomes. So the probability of 1, 1 over 10. 10% of the time we get 1. 2 over 10 is 20%. 20% of the time the outcome is 2. So that's our probability function there. Now, a cumulative distribution function. Remember we talked about cumulative distributions previously, and we're saying, well, the cumulative distribution function gives the probability of being less than or equal to a particular value. So for our probability function, p of x, f of 3, and that's our notation for the cumulative distribution function. So f of 3 is the probability of getting a value of 3 or less. So we're going to add up the probability of getting 1, the probability of getting 2, and the probability of getting 3. So 60% of the time we'll get 3 or less. And that makes sense because the probability of 4 over 10, is 40%. Oops, squeeze a 0 in there, 40%. So let's use that to do a calculation here. So for this example, the percentage return on equity, and that's our variable x, for a firm is defined over the range minus 20% to plus 30%. And we're given this cumulative distribution function. So for every value of x, it's x plus 20 over 50 is our CDF. So note first off, if we look at our upper bound of 30 here, if we plug in 30 here, we get 30 plus 20 over 50, 50 over 50. So that's 1 or 100%. And we're just saying there that the probability of being less than or equal to our maximum value is 100%. So now we're going to use this concept to answer the question, what is the probability that the ROE will be positive, so greater than 0, and less than or equal to 15? Well, Let me draw a picture of what we're doing here. Use my famous drawing skills. That's supposed to be a symmetrical normal distribution. Doesn't have to be normal for our purposes here. And so let's say that 0 is here and 15 is here. So the way we're going to solve this using this cumulative distribution function is first we're going to find the probability of being less than or equal to 15. So we'll plug 15 into our CDF. And then we want it to be positive as well. So we want to take off the negative. So then we're going to subtract the probability of being less than or equal to 0. And that will give us the probability of being between 0 and 15. So our probability, we're going to take F15, probability of being less than 15, we're going to subtract off the probability of being less than 0. So once we've framed the question that way, it's pretty straightforward to just put in our value for f of 15, 15 plus 20 over 50, that's 70%, and the probability of being less than or equal to 0 is 20 over 15 equals 40%. So we'll subtract 40% from 70%, and that puts 30% in that range between 0 and 15. So that's a way we might use this cumulative distribution function value, or values, in order to figure out the probability of being within a certain range or interval of our overall probability distribution. A discrete uniform distribution, the uniform part means that each outcome has the same probability. And discrete means we've got our countable number of possible outcomes. So, given that the probability of x equals 20% for each of our 5 possible outcomes, so we've got a total of 100% there. And so what's the probability of 6? Well, the probability of any of those 5, since they're equal, is 20%. So probability of 6 is 20%, probability of 4 is 20%, probability of 10 is 20%. So uniform. Now if we look at f of 6, that's our cumulative distribution function. Well, what's the probability of getting a value of 6 or less? Well, that includes 3 of our possible outcomes, and each outcome has a probability of 20%. So the probability of getting 6, 4, or 2, our cumulative frequency, is 60%. And if we want to look at a range specifically, that is 2 to 8 inclusive here, well, that's 2, 4, 6, and 8. That probability is simply 4 times 20%, or 80%. So that's a discrete uniform distribution. Our next distribution we want to talk about is a binomial distribution. Now, binomial distribution, one of the keys to it is there's only 2 possible outcomes. And each trial is called a Bernoulli random variable. A Bernoulli random variable takes on one of 2 values, say 0 or 1. Only 2 possible outcomes. Now we're going to do multiple trials here for our binomial. So we'll end up answering the question, well, in 5 trials, what is the probability of getting 4 successes out of 5 trials or something like that? So we have to define one of the outcomes of the Bernoulli random variable as success. Doesn't matter which one, may depend on the context of the problem. So the probability of success on each trial is constant. And They're independent. The outcome of one trial doesn't tell you anything about the outcome of another. So we could talk about how many times you get heads flipping a coin 5 times. So each flip of the coin is a Bernoulli random variable. The probability of getting 4 heads out of 6 flips of the coin is a binomial random variable. So the probability of exactly X successes in N trials is given by this formula here. Now, let me give you a little explanation which may help you remember this formula. Let's say that we've got 3 trials. So N equals 3. And we want the probability of 2. 2 successes in N trials. Well, say we've got a big barrel of balls. It's got white balls and black balls in it. And there are 60% black balls and 40% white balls. Well, what's our probability of getting a black ball in a single trial? Only 2 possible outcomes, right? White and black. What's the probability of getting a black one? Well, chosen at random, the probability of getting a black one is 60%. So let's call that the success. Okay? And we want the probability of 2 successes in 3 trials. Well, how could we get this? Well, one way we could do that is to choose black, black, and then a white. 2 successes in 3 trials. What's the probability of that? Well, these are independent. Remember, for independent random variables, our joint probability, we can just multiply them together. So the probability of that is 0.6 times 0.6 times 0.4. Probability of a black one times the probability of a white one, 40%. So we can rewrite that, if I got some room here, I'll rewrite that as 0.6 squared, because there's 2 of them, times 0.4, because there's 1 of them. Well, we could also get 2 successes in 3 trials by choosing a black one, a white one, and then a black one. What's the probability of that? Well, it's going to be exactly the same. We've got 2 black ones, that's 0.6 squared, and we've got 1 white one, that's 40%. So the probability of getting black, white, black is exactly the same as the probability of getting black, black, white. And what other ways could we do that? Well, we could go white, black, black. And again, the probability is 0.4 times 0.6 squared. So now look at this part of the formula. This is the probability of success to our number of successes. That's 0.6 squared here. And 1 minus 60% is 40%. N minus x, well, n we had 3 and 2 trials, so that's simply 0.4 to the 1 power 1, 0.4. So that's this part of the equation right there, the probability of getting these. What this term is here, this is our combination, N choose R. That says how many different ways are there to get 2 blacks in 3 trials? Well, we got 1, 2, 3 different ways. So this is simply the N choose R function right there. So probability of success to the power of the number of successes times probability of not success and the number of not successes times how many ways are there to get 2 black ones in 3 trials. Okay, now that we understand that binomial formula and probability, let's apply it to a different problem. Similar problem, what's the probability of drawing 3 black marbles from a bowl of white and black marbles in 5 tries if the probability of selecting a black marble is 0.6 each time? Well, let's take a look at that formula again to refresh your memory. We've got our n choose x term here, and we've also got probability of success to the number of successes, probability of failure to the power the number of failures in 5 tries. And so we've got x equals 3 here, n equals 5, and our probability of success is 60%. So given that, we put that into the formula, and the probability, or the number of ways to get 3 blacks in 5 tries, is 10. Okay. Here's our probability of success to 3, our number of successes, and 40%, the probability of failure, that is the probability of choosing a white one, is squared, because we're going to have 2 whites in 5 tries, and there's our probability right there, 34.56%. Now, a binomial random variable, a couple of properties you should be familiar with is one, what is the expected value of a binomial random variable? So it's just n times p, 5 tries. Okay. Probability of success is 60%. So our expectation is 3. Our variance is n, the number of trials, times the probability of success times the probability of failure. So as an example of that, consider the probability of an increase is 67%, and the probability of a decrease is 33%. So let's call increase our success here, so the expected number of increases in 5 trials is 3.35. That's our expected number of increases in 5 trials. So that's our expectation, or the meaning of this binomial distribution. So now we're going to use a binomial tree, because we will use this binomial model. I mean, it's going to come up on the level 1 exam, but it's also used at level 2. We use binomial trees to value options or value bonds with options embedded in them, like a bond with a call option. So you've got that to look forward to. But for that, we're going to need a binomial tree. And so here's our story. 2 possible outcomes each period, an up move or a down move. The probability of an up move plus the probability of a down move is 100%. One of those 2 is going to happen. And now we've got to have an up factor. The up factor is greater than 1, and we're going to multiply. Say we start out with a stock price. We're going to multiply that price times the up factor, if there's an up move. And then we've got a down factor that's less than 1. And we're going to multiply that stock price times the down factor, okay, for one branch of our tree. So as an example, consider a beginning stock price of $50. Our probability of an up move is 70%. Our probability of a down move then must be 30%. And we're given the up factor and the down factor. Our up factor is 1.1, our down factor is 0.909. So here's our tree. Here's our starting price here, $50. There's a 70% probability that over this first period, it's going to move up. And there's our up factor. So if it moves up from 50, it goes to 55. If it moves down, there's a 30% probability of that. It moves down from 50 to 45.45. And then we've got a second period here. Now, a binomial tree can be for many, many periods. For level 1, we're just focusing on how this works and how it's structured. So we're looking at a 2-period model. So in the second period, we've got the same game. Probability of an up move, 70%. Up factor, 1.1. So once we get to this node, once we've had an up move, the probability of an up move, well, they're independent trials, so it's still 70%. And we would have a price of 60.50. We've had 2 up moves, so we multiply by the up factor twice. That gets us to $60.50. And what's the probability of that? Well, we just go right out our branches. 70% probability of one up move, 70% probability of an up move in the second period, so a 49% probability of two up moves. And then we also could have a down move. So if we have an up move followed by a down move, well, the way we structured our up factor and our down factor, if we go up and then down, we get right back to 50. It doesn't have to be like that, but that's often the way we do it to simplify things a little bit. Well, what's the probability of 50 at the end of the second period? Well, there's two ways to get there. There's an up move followed by a down move can get us there, or a down move followed by an up move can get us there. So our probability here is 21%, up followed by a down, and the probability of a down followed by an up, well, that's also 21%. So 21% each route, two ways to get there, that gives us 42% probability of getting back to our original price here. And the probability of two down moves is 9%, 30% times 30%. And that would get our price down to 41.32. So where does the binomial formula fit into all of this? Well, that's where our probabilities come from. Because here we've got the probability of one up move in two tries, either up down or down up. So there's two ways to do it. We multiply probability of up times probability of down. And so that's this 42%. That would come from this binomial formula. So if we had a much more complicated tree, we'd really need to use those to calculate our probabilities. Probability of two up moves, 49%. Probability of two down moves, 9%. And they add up to 100%. That covers all of our possible outcomes. So that's how we'd construct a binomial tree. We end up after two periods with three possible outcomes, and we know the probability of each outcome. Well, we had the discrete uniform distribution, right? We had a given number of possible outcomes, and they each had equal chance. Well, what about with a continuous distribution? A continuous distribution, remember, it can take on any of these values, but we do establish the range here. We say, well, this variable is continuously uniform over the interval 2 to 12. Well, if you think about the probability as being the height of these things, okay, and then we have, I'll put probability there. And how many do we have? Well, this is 10 wide here, right? 2 to 12 is 10 wide. So we've got 10 boxes there. And we know that the total outcomes have to be 100%. All the intervals have to add up to 100% because that's the only range. The only values that this can take on is between 2 and 12. So if we put 10% here, 10% here, all the way across. We got 10 boxes, 10% probability. That's the uniform part. So now let's ask a question about this and see if we can answer it. The probability of x being less than 2 equals 0. That makes sense. The probability of x being greater than 12, that's also 0. We can't go outside the range. What's the probability of being between 4 and 8? So here's 4, and here's 8. Well, if we have 10% in each box, that's 40%. Another way we can look at it is 8 minus 4, that's 4 wide. The whole thing is 10 wide, so we've got 4 over 10 is the probability of being there. Now we can formalize that a little bit, but here we've got 8 minus 4, 4 wide. We're looking for probabilities in this range, 4 wide over a total of 10 in our range. we get 40% is our probability of x taking on the values between 8 and 4. Now, one thing I should mention at this point, for a continuous distribution, the probability of any single outcome is 0. And the reason is we have an infinite number of different outcomes. So for a continuous distribution, I can't talk about the probability of x here taking on the value 6.1126574. It's 0 because there's an infinite number of possible outcomes. What we can talk about with a continuous distribution is the probability of being within some interval. And that's what we're doing here.